Okay, so we are in causal inference in statistics, this book right here, and we are on question 1.5.3. Um, so, so here's the question. So consider a graph, a DAG, that looks like this, where x1 affects x2, x2 affects x3, x3 affects x4, and they're all binary random variables. So in other words, each one of these can take on a value of 0 or 1. And apparently the value of each of these variables, except for x1, is dependent, probabilistically dependent on the previous one, right? So x3, its value depends on x2 a little bit, possibly. So those dependencies, we're supposed to assume that they are described by these conditional probabilities, such that the probability that xi, so call it x3, given the previous variable x2, so xi minus 1, I need to go back and reformat this, so it should say x subscript I minus 1. But anyway, that equals p, and then the probability that one of the x variables equals 1 given that the previous one equals 0 is q. Okay? And of course, x1 doesn't have any predecessors, and so its probability of being 1 is called p naught. Okay, so I've gone back through and fixed these guys here. Okay, so we're supposed to compute the following probabilities, and so this one, this one, this one, this one. Okay, so we'll do these in turn. So first we'll just start with this big joint probability distribution that x1 equals 1, x2 equals 0, x3 equals 1, x4 equals 0. Okay, so that's all contained in this kind of shadow highlighted box here. So so what we want to do is one way that we could go about this, and the way that the book is encouraging, is to decompose this according to the DAG, right? So the way that we might do this is we might say, okay, well, what is the probability that x1 equals 1 times the probability that x2 equals 0, given that x1 equals 1, and notice how that mirrors this causal structure implied by the DAG, right? We have x1 has no predecessors, x2 is dependent on x1, okay? X3 is dependent on x1 and x2, and x4 is dependent on all its predecessors. Okay, but actually the fact, this is a little bit of a misnomer to say that x3 is dependent on x1 and x2, because all of the influence of x1 on x3 is routed through x2. So we could actually simplify these terms, right, as just being these 2x terms, right? So probability that x2 equals 0 given x1 equals 1, and then the probability that x3 equals 1 given that x2 equals 0, right? And that x4 equals 0 given that x3 equals 1, okay? And again, the reason that we're allowed to do that is because, so take this term right here, x3, whereas we had initially written it as x3 equals 1 given x1 equals 1, x2 equals 0. The effect of x1 on x3 is completely dependent on or mediated by x2. So once we know x2, knowing x1 doesn't give us any more useful information, so we can just drop x1 from our term there. Okay. So now our big joint probability distribution looks like this. Okay. And now we want to put this in terms of the p's and q's and p naughts. Okay. And so that's just matching all of this. Okay. So the probability that x1 equals 1, well, that's given to us as p naught. Okay. The probability that any variable equals 0 given that the previous one equaled 1, or equals 0, yeah, I said it right, okay. It's not p, it's 1 minus p, right? Because here we have the x2 equals 0 given that the previous one equaled 1, right? So so this is not p, it's 100% minus p. Okay, so we get that. And then similarly for q, what is q here? Okay, so now the probability that that a variable equals x1 given that its predecessor was 0, well, that's q. Okay, and then again and then we have the probability that a variable equals 0 given that its predecessor equals 1. We've already seen that. It's 1 minus p, so we get this. And notice we have two 1 minus p terms, so we can just take 1 minus p squared. Okay, so there's that one. Okay, so now we're going to a conditional probability, the probability that x4 equals 1 given that x1 equals 1. Okay, so this is interesting because x4 does depend on x1, but the effect of x1 is being mediated by x2 and x3. Okay, so well, we have to find a way to deal with that. All right. So first, let's just rewrite this in terms of the definition of a conditional probability, which is just the joint probability divided by the conditioning probability. Okay. Well, with both of these probabilities, this is the same as taking our big joint probability distribution up here, or something like that. Okay, and then just marginalizing out the variables that are not part of our statement, right? And that's x2 and x3 in this case, right? So we have the probability, the joint probability that x1 equals 1, x4 equals 1, and then x2 and x3 where we marginalize over x3. In other words, we account for all possible values and combinations of x2 and x3, okay? Divided by the probability that x1 equals 1. Okay, so this numerator we can expand out into 4 different terms, right? So we have probability that x1 equals 1 in each of these terms, that x4 equals 1 in each of these terms, but then in the middle for x2 and x3, again, we want to account for every possibility of x2 and x3. So we have 0, 0, 1, 0, 0, 1, 1, 1. Okay? So now we have these joint probability distributions that, again, we can decompose in a very similar fashion to as we did here in the first part. Okay? You know, right, where we basically try to mirror the causal structure implied by the DAG. Okay, so you can see how I've done that here. Okay, so each one of these joint probability distribution terms has this chain of probabilities corresponding to it. So I suggest that you look at that and work it out for yourself, and also make sure that I haven't made mistakes, because you know there's a lot of tedious typing and putting this problem together. Okay, well, and now with each of these terms here, we can find the corresponding, you know, PQ or 1 minus P or 1 minus Q term. Okay, and that's what we have here. And then I can simplify it a little bit, and this is the simplified version right here. Okay, the denominator P1, the probability that x1 equals 1, well, that's just called P naught. So this right here is our final solution or expression. Okay. Now for the next part, we have a very similar looking expression to what we had up here, but instead of finding the probability that x4 equals 1 given x1 equals 1, we're trying to find the probability that x1 equals 1 given that x4 equals 1. Okay, so this is going, where's our DAG? Here it is. So this is actually going the other way. We're trying to deduce the probability that x1 equals a value given one of its children's value, or its descendant's value. Okay, but the process is very much the same as what we just saw in the previous part. Okay, so we first convert it into these joint probability distributions, marginalizing over the variables that are omitted from the expression. Okay, and so this expression right here is, we've already found that in the second part. Okay. So we won't find that again. Okay, so I'm just copying and pasting it. Okay, but now the denominator is no longer a simple expression of P naught. It's the probability that x4 equals 1. Okay, and so how do we find that? Well, we have to marginalize over every variable that is not included in oh, that should be probability that x4 equals 1. Let me fix that. Okay, so we need to marginalize out every other variable. Okay, so that's what this is. Okay, so again, I can decompose this into all of the joint probability distributions for every combination of x1, x2, and x3, where x4 is always equal to 1. Okay, and so that's what I've done here. And again, each of these implies a chain of conditional probabilities, right? So again, we can correspond each one of these to one of these. Okay, so again, you should do that for yourself or check my work, because like I said, there's a good chance that I've made a mistake somewhere in here just in trying to type everything. And then all of this, each one of these terms, again, can be put in terms of the parameters p and p naught and q and 1 minus all those things. Okay, so the denominator ends up being this. And so when I combine that then with the numerator that we previously found, we get this big ugly thing right here. Okay, this could probably be simplified if we wanted to take a lot of time to do it, but you get the gist. Okay, I think that this is the final part. So now we want to find the probability that x3 equals 1 given x1 equals 0, x4 equals 1. Okay, so again, we decompose this into just the definition of a conditional probability, which we've done here, right? And then we want to find expressions for both of these. Okay, so to do that, so for this top term, notice that we don't have x2, so we want to take the joint probability where we marginalize out x2, so that's what we're doing here, and we'll look at that separately. And then in the denominator, we're marginalizing out x2, x3, and that's here. Okay, setting x1 and x4 to definite values. All right. So for the numerator, again, we're just marginalizing over x2. Okay, so we find we set x1, x3, and x4 to the values that were given, and then we marginalize over both values of x2, which is 0 and 1. We add those together. Okay. Again, this can be broken down into a chain of conditional probabilities, and each one of these conditional probabilities has a corresponding p or q or 1 minus p or 1 minus q term, dot, dot, dot. Okay. And so this is what the denominator looks like ultimately. Okay. And then a similar chain of reasoning then for the denominator. Okay, so by this point you should be getting pretty good at it. Okay, so we marginalize over every combination of values for x2, x3. So in each of these we have x1 equals 0, x4 equals 1, and then every combination of x2 and x3. Each of those can be broken down into a chain of conditional probabilities, which have their corresponding, p and q terms. Right. So now when I combine my numerator and my denominator, I get this expression right here. Okay. Again, you should really check all of this work. There's a high probability that I've made a mistake somewhere. If I have, please alert me. That would be great. But other than that, we'll call that good.